With this video, we conclude our unit on chemical bonding by talking about hybridization and the localized electron model, which is based on chapter 9.1 in the textbook. The localized electron bonding model is used to describe bonding and structure in molecular compounds, and there are three parts to it, or steps. Part 1, draw the Lewis structure for the molecular compound, including multiple bonds if they have them, including resonance structures if it exhibits resonance, and assigning formal charges to evaluate non-equivalent resonance structures. Step 2 is to name the molecular geometry using VSEPR theory, specifying bond angles, and then state whether the molecule is polar or nonpolar based on the geometry. And then finally, the third part is to state the hybrid atomic orbitals used by the central atom to explain that geometry. And that is the topic of today's video, hybridization. So let's begin by considering methane. What is the geometry of methane, CH4? Draw the Lewis structure. You'll see it's an AB4 type molecule, and that will let you predict correctly that it is a tetrahedral molecule. The bond angle is 109.5 degrees. How are the bonds formed? Well, the four carbon-hydrogen bonds must be formed by overlap of valence orbitals on carbon and hydrogen. What kind of orbitals must carbon be using to form these bonds? Well, it only has two s and two p orbitals. Why is that a problem? Well, the problem is, how do we explain the 109.5 degree bond angle when all we have are s and p orbitals? The s orbitals are non-geometric, the p orbitals are 90-degree angles, so we use the concept of hybrid atomic orbitals. Hybrid atomic orbitals are a model that was developed in the 20th century. They are atomic orbitals that are formed by linear combinations of s and p orbitals in the valence shell of an atom, and we use them to explain the observed bond angles in molecules that do not correspond to the angles between s and p orbitals. So, here's how it works. I am going to draw an energy level diagram for the valence orbitals of carbon and methane. On the left, and we see in the ground state, there are 2 electrons in the 2s sublevel and 2 electrons in the 2p sublevel. I will take these 4 unhybridized atomic orbitals, combine them in a process called hybridization to form 4 new equivalent sp3 hybrid atomic orbitals, indicated on the right. Each of those 4 equivalent sp3 hybrid atomic orbitals now accommodates 1 unpaired electron. And here is what they look like. I take the 2s, the 2px, the 2py, and the 2pz atomic orbitals on carbon, and I combine them mathematically to form 4 new sp3 hybrid atomic orbitals, as you see on the right. And what do you know? Those hybrid atomic orbitals point at angles to one another of exactly 109.5 degrees. And here's how we now explain the tetrahedral geometry in carbon. Each of the large bluish-purple blobs represents one of the sp3 hybrid atomic orbitals, and as you can see, they are pointing exactly towards the corners of a regular tetrahedron. Each of the pinkish-purple spheres represents the 1s orbital on hydrogen. Each hydrogen brings in 1 electron. Each of the 4 sp3 hybrid atomic orbitals on carbon contains 1 electron. They overlap to form our 4 carbon-hydrogen bonds. So, anytime the central atom has 4 electron pairs that are pointing towards the corners of a tetrahedron, we say that it is sp3 hybridized. Why sp3? Because they come from 1s and 3 p's. What about ammonia? Well, ammonia has 4 electron pairs pointing towards the corners of a tetrahedron. In the ground state of the nitrogen atom, we have 2 electrons in the 2s sublevel, and we have 3 electrons in the 2p sublevel. Once again, because there are 4 electron groups around the central atom, we combine the atomic orbitals to form 4 equivalent sp3 hybrid atomic orbitals. Now, as you see, we have 5 electrons. One of the sp3 hybrid atomic orbitals has a pair of electrons, whereas the other 3 have 1 unpaired electron. Does that make sense? It makes perfect sense, because the 3 singly occupied sp3 hybrid atomic orbitals are used to overlap 1s orbitals on hydrogen to form the 3 equivalent NH covalent bonds. The sp3 hybrid atomic orbital that contains the pair of electrons becomes the lone pair on nitrogen. Isn't that cool? And here's what it looks like. Okay. Again, the large blue blobs are the sp3 hybrid atomic orbitals on nitrogen. The small pinkish purple spheres are the 1s orbitals on hydrogen, and up top we see the sp3 hybrid atomic orbital that contains a pair of electrons that corresponds to the lone pair. Once again, any atom with 4 tetrahedrally arranged electron groups around it, we say it uses sp3 hybrid atomic orbitals, or we describe the hybridization as sp3. What about borane, BH3? Draw the Lewis structure. You will see that borane is trigonal planar, and it has bond angles of 120 degrees. Once again, how do we explain this bond angle? Well, we will use hybridization of a slightly different sort. We will start with boron, which contains 3 electrons, 2 in the 2s and 1 in the 2p. We will combine now the 2s sublevel and 2 of the 2p atomic orbitals to form 3 sp2 hybrid atomic orbitals, each of which contains 1 of the electrons. Now, boron has 3 electrons it can use to form the 3 BH bonds. The remaining 2p orbital remains unhybridized. It does not change. It's still there, it's just empty. And once again, this is how we explain the trigonal planar geometry. We take one s orbital and 2 of the p orbitals, we hybridize them, and we form a set of 3 equivalent sp2 hybrid atomic orbitals. What do you know? They point exactly towards the corners of an equilateral triangle. That's how we explain trigonal planar geometry. Once again, sp2 because it comes from 1s and 2p. Okay. So, anytime we have an atom that has 3 electron groups around it that are oriented in a trigonal plane, we say it uses sp2 hybrid atomic orbitals, or we describe the hybridization as sp2. And here you see the 3 equivalent sp2 hybrid atomic orbitals in green in the plane of the molecule, and you see the unhybridized p orbital that remains perpendicular to that plane. Now, this leads to the concept of sigma and pi bonding. Sigma bond is a covalent bond that is formed by head-to-head overlap of atomic orbitals, and it is therefore cylindrically symmetrical, whereas a pi bond is formed by side-to-side overlap of parallel unhybridized p orbitals on adjacent atoms that are sigma bonded to each other. And here's what it looks like. The green lobes represent a sigma bond formed by head-to-head overlap of some sort of atomic orbital on carbon. Each of these 2 carbons has an unhybridized p orbital with electron density above and below the plane of the molecule. That side-to-side overlap of the unhybridized p orbitals, containing 1 electron each, is the pi bond. The pi bond is the second bond of a double bond. Okay? So, this is how we explain bonding in ethene, H2CCH2. Let me draw a Lewis structure of that just so we know what we're talking about. Okay. So, C2H4, we've got a carbon-carbon double bond and 4 carbon-hydrogen single bonds. The 5 sigma bonds that make up the sigma framework are formed by overlap of sp2 hybrid atomic orbitals on carbon with the sp2 hybrid atomic orbital on the other carbon and with the 1s orbitals on hydrogen. This molecule is in the plane of the board, but remember, on each carbon atom perpendicular to that plane is an unhybridized p orbital that contains an electron. And as a result, those unhybridized p orbitals, shown in blue here, overlap in a side-to-side fashion to form the pi bond, which is the second bond. So here we see formation of the pi bond by side-to-side overlap of parallel unhybridized p orbitals on adjacent sp2 hybridized carbon atoms. So a single bond is made up of 1 sigma bond. A double bond, as we saw in ethene, C2H4, is made up of 1 sigma bond plus 1 pi bond. What's a triple bond made up of? You guessed it, 1 sigma bond and 2 pi bonds. Finally, let's move to carbon dioxide. What's the geometry of carbon dioxide? Of course, it's linear. It has a bond angle of 180 degrees. How do we explain the bond angle? Once again, we're going to use hybridization. So here's our energy level diagram for carbon. We will place 2 electrons in the 2s sublevel, 1 electron in the 2p sublevel. We will now combine the 2s orbital and 1 of the 3 2p orbitals to form 2 sp hybrid atomic orbitals, okay, each of which will contain 1 electron. The remaining unhybridized 2p orbitals will also contain 1 electron each. Okay? Why do we call them sp hybrid atomic orbitals? Because they're made up of 1s and 1p. And here's what it looks like. We take the 2s and 1 of the 2p orbitals, let's say the 2pz, and we form sp hybrid atomic orbitals, and wouldn't you know, the angle between the sp hybrid atomic orbitals is exactly 180 degrees. Okay, this is how we explain linear geometry. So here in carbon dioxide, we see in yellow the two sp hybrid atomic orbitals on carbon. Each of them is overlapping an sp3 hybridized atomic orbital on an oxygen, shown in green. That forms the carbon-oxygen sigma bonds. But the carbon, remember, has those two unhybridized p orbitals, one pointing up and down and one pointing out and back, each of which contains an electron, and each of those can overlap with an unhybridized p orbital on one of the oxygens, forming the second bond of each of these two carbon-oxygen double bonds. So anytime an atom has two linear electron groups around it, we say it uses sp hybrid atomic orbitals, or we describe the hybridization as sp. Now, here's a summary from the textbook. Remember, all we're doing with hybridization is labeling the molecule. We look at the Lewis structure, we assign the geometry using VSEPR. If there are two electron groups around the central atom at an angle of 180 degrees, we say it's sp hybridized. If there are three electron groups around the central atom that are 120 degrees apart, we say it's sp2 hybridized. If there are four electron groups around the central atom with an angle of 109.5 degrees, we say that it is sp3 hybridized. Now, you may be tempted to ask, well, what about AB5 and AB6 molecules, molecules with expanded octets? Older textbooks describe using d orbitals, but that is no longer in vogue. That is not considered to be correct. So according to the AP curriculum, we are only going to use hybridization for molecules in which the central atom obeys the octet rule. We will not invoke hybridization with hypervalent molecules. Okay, so let's do some examples. For each of these, we are going to state the hybridization on the central atom. And as you can see, I've already done the Lewis structure and the molecular geometry. Arsenic trifluoride is trigonal pyramidal. I see four groups of electrons around the central atom, which will be pointing towards the corners of a tetrahedron. Anytime there are four groups, we say it is sp3 hybridized. Carbon disulfide is linear, bond angle of 180 degrees. Anytime that's the case, we say it is sp hybridized. Sulfur trioxide is trigonal planar. The three electron groups around the sulfur are arranged pointing towards the corners of an equilateral triangle, or trigonal planar. So we're going to describe the hybridization of sulfur as sp2. And finally, germanium tetrabromide is tetrahedral. We've got four electron groups around the central atom. That would be described as using sp3 hybrid atomic orbitals. Essentially, the hybridization, if you sum up the exponents, that's equal to the number of groups of electrons around the central atom. And we will skip those because those do not apply. Here's a Lewis structure of a kind of complicated organic molecule. State the hybridization of each carbon atom and specify the number of sigma and pi bonds in the molecule. I see one carbon atom that is forming four bonds. So that is sp3 hybridized. I see 1, 2, 3, 4, 5, 6 carbon atoms that have trigonal planar geometry. I should have said the first carbon, it has tetrahedral geometry. I see 6 that have trigonal planar. So those are sp2 hybridized. And finally, I see 2 that have linear geometry, and those are going to be sp hybridized. Now, in order to count the sigma and pi bonds, every single bond is a sigma bond. I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I think I counted that correct. Every double bond contains one pi bond. Every triple bond contains two pi bonds. So I see 3 double bonds and one triple bond. 1, 2, 3, 4, 5. That makes 5 pi bonds. And that is our unit on chemical bonding.